And here's the last lecture for this section. We are going to look at an example of multivariable function. So far, we've only looked at examples of functions with single input and a single output. But we could also have a function that needs more than one input. For example, a function requires x and y, or x, y, and z. We could have as many inputs as we need. Also, the outputs, so far we've only covered when the output is only a number. But we could also have functions that give us an output that is a pair of numbers, or a triple of numbers, or quadruple, as many outputs as we need. But that does not mean that we have to violate the definition of functions. The definition of function is an input will give us exactly one output. But when I said we could have multiple outputs, I mean an ordered pair of numbers. Similarly to coordinates, I define a point by 1 and 2, when x equals to 1 and y equals to 2. So that is 1 point. But to describe this point, I need to have two coordinates, x and y. And if we are in a three-dimensional world, then we need x, y, and z. So to describe a point, I need 3 coordinates, or even 4, the time. So I need x, y, and z, and the time. So they are an ordered pair of numbers to describe a single point in the space. Let's look at this example. Part A, explain why the rule P that maps from R to R cubed, defined by P of t, 3t, t squared minus 1, and t is a function. Then find P of 2. Let's first understand the notation. The rule P maps from real number to R cubed. The first set of numbers means the domain. That means the input is only one number. And this function will map the one number to a three-dimensional space. So the range is R cubed. The cube here means that the output is an ordered triple of real numbers. So is P of t a function? The answer is yes, because for each input, it's sent to the function exactly one triple of real numbers. Now let's find P of 2. P of 2. So I substitute t, the input, by 2. Then the triple of numbers I'll get would be 3 times 2. So that's the first coordinate of this triple of numbers. And the second component would be 2 squared minus 1. And the third component is t. So the triple of numbers of this output is 6, 3, and 2. Now let's look at part B. Explain why the rule Q that maps from R squared to R squared, defined by Q of x and y, that equals to x minus y and negative 3x, is a function. Then find Q of 3 and 2. Let's understand the notation of the rule. The rule sends from R squared to R squared. The domain is R squared, which means we need 2 inputs. And the output is also R squared, which means the output will be a pair of numbers. And is this rule a function? The answer is yes, because for each pair of the input, x and y, the function will give us exactly one pair of numbers. Now let's find Q of 3 and 2. Q of 3 and 2. So I'm going to replace x by 3 and y by 2. So I'll get the first component would be 3 minus 2. Since in the function I have x minus 1, and the x here is the 3, and y is the 2. X is the 3, and y is the 2. Then the second component, I have negative of 3x. X is 3, so the second component of the output is negative 3 times 3. So Q of 3 and 2 is 1 and negative 9. And that is the end of the section. This section we covered functions and graphs. After this lecture, you'll find an assignment on this section. You can take your time to complete the assignment without looking out for the solutions. After you submit the assignment, the solutions will be provided. In the next section, let's dig into functions and let's look at the operations, transformations, and inverses of functions.